Welcome to the Cosmic Savannah with Dr. Daniel Kahneman,
Francois Camphor,
and Dr. Jacinta Delhaze. Each episode will be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Hi everyone, welcome to today's episode.
Hey Jacinta.
Hello.
Hi.
And just to announce, we are, for those listening online, we are back in the original studio that Jacinta and I began this whole thing in. And wave to the camera if you're watching online.
Yeah.
Our tiny little studio. I think some of you may have seen it on social media a long time ago. We're sitting inside the old Pendulum Room at the SAO. And in a tiny little dusty room.
It's very different to the one-button studio that you, if you've been watching on YouTube the last few episodes, you will have seen. We're back in our roots just for nostalgia's sake. And we very kindly have some amazing videographers who have volunteered to join us today. And they have hitched a camera up somehow magically to a metal rod in the roof, and it's a very wide angle lens because this room is teeny tiny. Anyway, so that's where we are. Tiamiso is unfortunately not able to join us today, but that's kind of fortunate because we can't fit 4 people in here. But anyway, so the one button studio is all booked out. That's why we're in here.
Well, also I think, like Francois said, a nice farewell to the Pendulum Room.
It is, but we might need to use it again. So I don't know if it's a farewell.
Anyway, so today's episode, we are talking with Dr. Simon de Vet, who works on gamma ray bursts, and he'll tell us all about what he found out during his PhD.
So Simon has now moved to?
Copenhagen.
Yeah. Right, okay. Where he's doing a postdoc.
Yes. Yep.
At DTU. He's... I believe he's studying transients now, so supernovae mainly, but in today's episode we'll mostly be talking to him about his PhD and master's work, which is all on gamma ray bursts.
And who wants to go first?
Okay, well, I'll ask the questions here because I don't know anything about gamma ray bursts. So, right, first of all, I'm going to ask Francois first because I know Francois works on transients and gamma ray bursts are classified as transients, I'm going to assume. So GRBs, gamma ray bursts. Francois, what is a GRB?
A GRB is basically an incredibly bright burst of light energy from space that is usually the result of either a collapse of a very massive star, which is like 20 times the mass of the sun, or of what, we think it is it could be caused by 2 neutron stars orbiting each other and eventually colliding, forming a black hole. So basically, in both cases, a black hole is formed, and from this violent formation, these incredibly bright bursts of light get shot into the universe. And when I say bright, okay, I read this last night about GRBs. The average GRB's amount of light that it produces is equal to the total light of the sun over its 10 billion year long lifespan.
Whoa.
Yeah.
If you add up all of the energy
that the sun ever emits, ever.
And that's the average energy of a GRB.
What, in 2 seconds or something?
Yes, in 2 seconds.
But then that's obviously spread over a huge distance, which is why we can see them from very far away.
Exactly.
So when these gamma ray bursts are happening and we're observing them, they're things which are happening very far from us, not like the sun.
Incredibly far. Yeah, that's why we are all alive. Because they are all, so far at least, most of the ones that we've discovered are decently far away enough so that the ozone layer can protect us from the gamma ray bursts. In fact, gamma ray bursts happen quite frequently. We see at least about 1 or 2, I think, a day is the average detection.
Oh, really?
It depends, but the frequency is quite high. So basically, in space, your chance of surviving has gone down again. I know it's low already, but at this point it is impossible, right? So luckily for us, we have an ozone layer, which protects us from the gamma ray bursts mostly. However, that is only because they are decently enough far away, so the light is spread out enough for the ozone layer to protect us. But if one were to go off within our galactic neighborhood, well, we'd be done for, basically.
Yeesh.
It'll be quick.
Yeah, exactly.
Yeah.
And we won't know until it happens, so it's fine.
And then you won't know any either. So,
Yeah.
Basically, you'll never know.
Pretty much.
Okay.
So detecting these gamma rays, we can do that from Earth.
Yes.
But as you said, the ozone stops them. So what happens is you set up these arrays, these gamma ray telescope arrays, which detect the cascade of highly charged particles. So the gamma ray hits the ozone layer, the upper atmosphere, and explodes into, splits into many different particles, which then cascade down to the surface of the Earth. And we kind of reconstruct that car crash to work out where the thing came from.
So what kind of is it an optical telescope, or like what kind of telescope detects that cascade?
Yeah, so so these gamma ray bursts are coming into the upper atmosphere, as you said, like they're hitting the ozone layer and the particles there. So then it's a question of how we detect them. So in space, a gamma ray telescope in space can detect them, using not regular, but like a gamma ray telescope, and it's detecting the actual gamma ray light. But because the gamma rays don't pass through the atmosphere, we have to build these arrays of detectors of the secondary light. So what happens is the gamma ray hits the upper atmosphere, and it passes its energy into a cascade of particles, which then come down towards Earth, and those particles emit a faint glow, like a blue glow. So then the telescope can detect all of these particles and reconstruct the car crash that happened as the thing hit the upper atmosphere, and try and work out which direction it came from.
Yeah, we talked about that a bit in a previous episode with Dr. Eli Kasai from Namibia about HESS, the high energy
Spectroscopic
stereoscopic.
Yeah, because it's stereoscopic, right? It's stereoscopic, so that it can work out the direction, right? So,
Sorry, I've temporarily forgotten, but check out that episode. We'll link it in the show notes. And that was also in preparation for the CTA, the Cherenkov telescope array, which is going to be built in the future. And you might notice if you're watching this on YouTube that I am no longer wearing headphones, and now Francois is
that's a good point.
wearing the headphones of shame because he's new to the studio, recording in here, and he's making too much noise. So now we've given him the headphones so he knows when he's making too much noise. I also continually forget that we're like on video now because we never have video in the studio. No. So I keep doing things like pointing to the mic.
That's great. It's good for the viewers. So if you're listening online, maybe go back and look at the video. Also, like Jacinta's hair after taking off the headphones is
Oh, no! Give me my headphones back. Are you joking or are you serious?
I'm serious. Of course I'm serious. Okay, but maybe we should actually get into Simon's interview before we rattle too much on gamma rays.
Simon did his PhD on GRBs, and he's the expert. So let's just hear from him. With me now is Dr. Simon de Vet from the University of Cape Town. Welcome to the Cosmic Savannah, Simon.
Hi, it's great to be here.
Tell our listeners a little bit about who you are, where you're from, what you do.
Yeah, so I was born and raised in Cape Town. I've done all my studies here at the University of Cape Town, and I'm an astronomer. Yes, you are.
So, Simon, you have just gotten your PhD in astronomy from UCT. So you have been one of our PhD students in the Department of Astronomy at the University of Cape Town, and you've submitted your PhD thesis after years of very, very hard work. And your thesis examiners passed it, and you've just had your graduation ceremony. So now you're officially doctor. Congratulations.
Thank you. Yeah, it's a great achievement. I'm very proud of it.
You should definitely be. How was your graduation ceremony?
No, it was just a fantastic day. Really, a lot of smiles, a lot of happiness. Yeah, and also a lot of relief.
I was going to say, surely relief as well. Yeah. So, Simon, today you're here talking with us in the studio. What do you think of our studio?
I really like it. It's a nice, quiet room. It's a good place to do some research.
You reckon? I've never thought of that, actually. It's a very strange place, but a very cool place. And we're really glad to have caught you for an interview now, because in a couple of days you're actually flying off to another country to take up your first postdoctoral research job.
That's correct. Yeah, on Sunday I'm going off to Denmark, and I'll be doing a 3-year postdoc at DTU in Copenhagen, the Danish Technical University. I'm very excited for that.
Wow, so you're moving to Copenhagen for 3 years.
That's correct.
Wow, that's so exciting. What will you be doing there?
Yeah, so I'll be continuing within time domain astronomy, or transient astronomy, which is the study of objects in the night sky which vary over a range of timescales.
So things that go bang in the night, basically.
Exactly.
Things that suddenly glow brightly, which weren't glowing before.
Exactly.
Okay. Awesome. So you're going to continue with that research in your first postdoc. So that's what you were working on for your PhD. Can you tell us a little bit more about what you were doing?
Sure. So over the course of my PhD, I was studying a particular category of explosion called gamma ray bursts. And these are, I guess their claim to fame is that they are the brightest explosions in the night sky. And they really are fascinating. I can talk for a long time about them.
Well, that's good, because that's what we're here to do. So GRBs, gamma ray bursts. I don't know where to start. What are they?
Yeah, so gamma ray bursts are essentially the brightest explosions in the night sky, and one should look to the name to see where, what these objects are. So gamma rays are the highest form of electromagnetic radiation, the highest energy form of EM radiation.
So they're a kind of light, right?
Exactly.
So optical light is a kind of electromagnetic radiation. And how does that differ to gamma rays?
Well, yeah, so optical light is also EM radiation, but it's much lower energy.
Mm-hmm.
So gamma rays they can actually penetrate through all kinds of materials, which makes them very, very harmful.
Mm-hmm. So they can be harmful to humans?
Indeed.
Okay, and these gamma ray bursts, are they harmful?
They would be if they were very nearby, for instance, in our galaxy. But most of them, pretty much all of them that we have observed, have been in very distant galaxies. So we don't have to worry too much about them actually harming us.
So do we think that gamma ray bursts have ever gone off in our galaxy, the Milky Way?
Well, it's actually quite interesting. Some people have put forward theories that say that some of the very large mass extinctions on Earth were in fact caused by gamma ray bursts.
Really?
Indeed, yeah.
Oh, wow. Okay, so wait, what? Does that mean, are we in danger?
Well, if one did go off in our galaxy and was pointed right towards us, yes, we'd all be toast.
Oh dear, okay. All right, so then, wow, that was blowing my mind. All right, so these are bursts of gamma rays, as the name suggests. All right, so how were they discovered? Maybe let's start there.
So they were actually discovered by accident in the 1960s. So what happened was the Americans put up a whole lot of satellites into space, and these were called the Vela satellites. And they were launched with gamma ray detectors aboard to see whether the Soviet Union, the Russians, were actually keeping to their part of the nuclear test ban treaty. Because a nuclear test on Earth would emit a whole lot of gamma rays that would be detectable by these satellites. So it was actually for almost espionage that they were sent up into space. And then after a few years, they discovered these mysterious bursts not coming from Earth, but coming from space.
Oh, and did they think it was atomic bombs or anything to begin with?
Well, they knew that it wasn't an atomic bomb because an atomic bomb test has a very particular signature. Which is quite different from the bursts that come from space.
Okay, so they were coming from space. So then what did they find?
They detected a very bright gamma ray source that would last for around a few tens of seconds. And over a few years, they detected quite a few of them coming from quite random parts of the sky. And essentially, for the first 30 years of the field of gamma ray bursts, people really didn't know where they were coming from. Were they coming from within our galaxy? Or were they coming from much further away?
Right, because so they were seeing these sudden flashes of gamma rays lasting up to tens of seconds. And we can see where they are in the sky, but we don't know like distance, because distance is so hard to study in astronomy and to understand distances in space. So they could have been close to us in the Milky Way, but they could also have been from galaxies far, far away.
That's correct.
And what was the answer?
Well, like I said, it took 30 years for us to actually figure out where these gamma ray bursts were coming from. And that was due to the discovery of the first counterparts at other wavelengths, in particular at optical wavelengths.
So when you say counterpart, what does that mean?
That means you see an object at the position of the gamma ray burst, but at a particular wavelength or energy. For instance, at radio waves, X-rays, or an optical light. You see light coming from essentially the same source.
Okay, so from the same position as where the gamma rays went off, you see suddenly you see a glow in the optical, you see a glow in the radio, and all of these other wavelengths of light. Okay, so this is called the afterglow. Is that correct?
That's correct.
And so presumably from the name, it comes after the gamma ray burst went off.
Exactly. Yeah. So there are these two types of lights that I guess come from gamma ray bursts. So you have the prompt emission, which is the gamma rays itself, and then very shortly thereafter you get the afterglow, which is radiation or emission from across the electromagnetic spectrum.
All right, so quick flash of gamma ray bursts, and then after that, then this glow at the other wavelengths. So you said it took them 30 years to figure out where these gamma ray bursts were coming from, and that happened once they found these afterglows. Why was that important?
The reason it took 30 years was that it was very difficult to localize gamma ray bursts. It was very difficult to find out where exactly in the sky they were coming from. And that is due to the gamma ray detectors themselves, which are rather crude in terms of localizing the source of gamma rays, which is in contrast to, say, an optical image of the sky, where you have very high resolution and you can separate objects nice and clearly.
Okay, so when you say localize, you mean to know exactly where it was coming from. So you might see gamma rays in like roughly that broad part of the sky, but you'd need something with a much higher resolution in order to figure out to have a much smaller area, to localize it to a much smaller area on the sky, therefore knowing exactly where it's coming from.
That's exactly right.
Okay, and so an afterglow was discovered, first with an optical telescope?
Well, actually, the first afterglow was discovered at X-ray energies, but then a few months later, they discovered the first optical afterglow.
All right, and then so what did that tell us?
Well, once you detect something in the optical, then you really can precisely pinpoint its position. And the optical light is really valuable because if you get take a spectrum of that optical source, you can actually figure out the distance.
Right, and a spectrum is when you use a telescope and you split the light into tiny little chunks in frequency or in wavelength, and then you can see particular features like what we call absorption lines. So basically you have gas and stuff absorbing some of the light. It's at tiny little frequency ranges. And if you can see exactly what frequencies these are happening at, it tells you the distance.
Exactly.
So by looking at this optical afterglow, that helped to pinpoint the position. So then they know, okay, let's point this other optical telescope with this spectrograph at that position. We can get the spectra. And then they found the distance.
Exactly, yeah.
And what was the distance? What did they find?
So what they discovered was that these gamma ray bursts were not coming from our own galaxy. They were actually coming from very distant galaxies in the universe at pretty high redshifts, I would say.
Okay, so not the Milky Way, very high redshifts, meaning very, very far away.
Indeed.
So then they know that the GRBs, the gamma ray bursts, are originating very far away. What do we actually think is causing the gamma ray burst? Like physically, what's happening?
Yeah, so I guess shortly after those very first afterglow discoveries, they noticed for a few gamma ray bursts that there was a supernova associated with the burst. And what that allowed us to tell was that the core collapse of like a very massive star is in fact related to the long gamma ray bursts.
Okay, so massive stars, at the end of their lives, they die in huge supernova explosions. So it's called a core collapse because the whole star collapses in towards the core, and even the core, like the center of the star itself, collapses, and then stuff rebounds in this big supernova explosion. And what can be left at the end of that is a black hole.
That's right, yeah.
So since you saw a supernova go off at the same position as the gamma ray burst and kind of shortly after. So then the conclusion is that GRBs maybe are caused by this collapsing star and the formation of a black hole.
Indeed.
Cool.
Yeah, no, they are related.
All right. So gamma ray bursts caused by the formation of a black hole. And do we know any more details about like what physically happens when this black hole's formed to create this gamma ray burst?
Sure. So our current best physical picture is that after the collapse of the star, you have a black hole, and material surrounding that black hole falls into the black hole, and it creates this very strong outflow or blast wave that is emitted from the black hole in two directions. And within that blast wave, you have light being emitted, and that is what we see as the gamma ray burst and also the afterglow. Yeah, and that's the fireball shock model.
Cool. That's a cool name. Fireball shock model. Okay, so now we know where GRBs come from and we have an idea of what's producing them. So what did you do in your research during your PhD?
Yeah, so the aim of my PhD work was to follow gamma ray bursts and try and catch their optical afterglows. In particular, I used the Meerlicht Optical Telescope, which is at Sutherland here in South Africa, a really great little telescope, which is very good at observing explosions. Yeah.
Cool. And yeah, tell me what you did with Meerlicht.
So Meerlicht, because it's fully robotic and it has 6 optical filters, we are able to rapidly point the telescope to the position in the sky where gamma ray burst has just gone off and obtain really nice optical data.
Okay, and what did you find?
So over the course of my PhD, roughly 2.5 years for which this program was running, we followed up, 29 gamma ray bursts, but in total, we saw 10 afterglows.
Oh, cool. So you had a look at 29 gamma ray bursts that had gone off, detected presumably with gamma ray telescopes. And then you went to those positions with Meerlicht and you were like looking to see if you saw any matching glow in the optical, and you saw it for what did you say, 10?
Yeah, I think roughly 10.
Cool.
About a third.
And was there anything interesting about it that you observed?
So we used Meerlicht to track the brightness of the object as it evolves in time. And, there's kind of like a standard light curve that one expects, but we observed some really unusual behavior for some of these bursts. And that's why we were able to write a publication.
Okay, so we have an idea of how bright this optical afterglow should be and how that should change over minutes and hours after, like once you first spot it, and it changes very, very quickly. And you observed that it wasn't quite changing the way that we expected it to, right?
That's correct. Yeah. So a big challenge of the follow-up of these gamma ray bursts is that they evolve very quickly. So you really need to get on sky very quickly to see how it's changing before it fades too much.
So it's a game of speed, basically.
Absolutely.
Okay, so Meerlicht, and you use Meerlicht in Sutherland. It can, like, this burst goes off, there's an alert that goes around, and then Meerlicht's able to, like, look really quickly at that point and be like, look, I got there really fast. And so then as soon as you get there, then it's already the amount of light is starting to change really quickly. And so that was your advantage, is like you got to spot what was going on just shortly after the gamma ray burst, right?
Exactly.
So this unusual, what you call a light curve, this changing pattern of the brightness over minutes and hours, what does that mean?
Well, if we see something unusual, it's, for one thing, it definitely requires further study. We want to know exactly what's going on with this explosion. Are there different physics at play? What's going on with the collapsed star?
So to be continued, right? We don't know yet.
No. So at this stage in the field, we want to observe as many gamma ray bursts as we can so we can put together the clearest picture we have of the physics of these explosions.
Right, because this is really quite a new research field, isn't it?
Yeah, I guess it started in 1997, and it really ramped up in 2004 with the launch of SWIFT, an amazing small NASA mission.
Telescope to detect gamma ray bursts, yeah?
Exactly.
Cool. So, yeah, it's a really exciting field, and not that many observations. And so your contributions are really, providing what we call observational evidence. We need to observe them, and we need to observe them as quickly as possible and for as long as possible and see what happens. So it's like providing more observational evidence so that hopefully we can build our physical models over time and try and understand the physics of what's going on in these systems. And you mentioned there was something else interesting about one of the afterglows you saw.
Yeah, so the last burst, which ended up as a publication, was really interesting because we got a whole host of radio data, including with the Meerkat radio telescope, which is also here in South Africa and one of the most sensitive radio telescopes in the world.
Oh, my favorite telescope. This is what I use for a lot of my research. Okay, so we know you can have afterglows in the X-rays. We know you can have afterglows in the optical. And so now you can have also afterglows in the radio.
Yes, and in fact, I would say even to this day, our understanding of radio afterglow emission is still in its infancy.
All right, so we don't understand why it's there.
Mm-hmm. Exactly. So, I mean, yeah, there are not as many bursts that are actually followed up at radio wavelengths. Also, they need to be quite bright for there to be radio emission. So that's what makes it quite challenging.
Okay, so you provided some more observational evidence by also getting the radio afterglow. Was there anything interesting about it, or we don't really know yet?
Yeah, in fact, it was a very unusual and interesting radio data set. So we got millimeter data with the ALMA array, which is in Chile, and by far the most sensitive millimeter observatory in the world. And then we also got radio data from ATCA, Australia Telescope Compact Array, and then Meerkat, like I mentioned, and also a telescope in India called the GMRT, the Giant Meter Wave Radio Telescope.
Cool. So you got radio data from all over the world. Did you find anything interesting?
Yeah. So what was really unusual was actually at millimeter wavelengths. In the ALMA data, we saw this very strange rebrightening, which has never been observed before. And so it was my job to try and explain, using physics arguments, what exactly is going on.
I know this might be a bit advanced, but what did you find? What do you think was the reason?
Well, what often happens in science is that there's no conclusive, there's no very firm conclusion. But I did put forward a few different explanations. One was that it could be a reverse shock, a blast wave or a shock wave moving back
towards the black hole.
The black hole.
Okay.
Yeah.
So that's your best guess, is like this kind of reverse blast wave.
Exactly.
Cool. That's really awesome. Well, that is all extremely interesting, Simon. Thank you so much for taking the time, especially in this busy period just before you emigrate to a different country, to speak with us and explain this really cool new field of astronomy to us. And before you go, do you have any final messages for listeners?
Yeah, I guess, based on my own experience, I just really encourage everyone, if you really are passionate and interested about something, just go full on into it, because it really can be so very rewarding.
Awesome. Throw yourself all the way in. Yes, again, congratulations on getting your PhD, your achievements, and for speaking with us today. Thanks very much, Simon.
Thanks very much.
So I thought it was really interesting hearing from Simon. A few things blew my mind, including that many of the mass extinctions on Earth may have been caused by gamma ray bursts.
I didn't know that.
I did not know that either.
Yeah.
That matches what you were saying at the start, Francois, about how if something went off close to us, we're in trouble.
Yeah,
and
we'd be toast.
Yeah.
Yeah, and I mean, I imagine things like the upper atmosphere, what it's made of has changed over the years. So maybe we've gone through periods where it's been slightly less protective. I mean, I don't know how it would play out, but I mean, I know how the once-off event would play out.
Yeah, it'd be quick.
Fried. But a mass extinction event where something survived. Anyway, this is not our area of expertise.
No, not at all. No.
Microbes would survive and have survived.
Yeah, some of them. I think that.
And we start from scratch again. Oh,
extremophiles, yeah.
She's like, oh man, we go back 4 billion years. Oh, all that effort.
Oh yeah. Simon was talking about one particular type of GRBs called long GRBs, right?
Yeah.
But if I understand correctly, there's also short GRBs. Is that correct, Francois?
Yes. So long is a relative term. Long just usually means greater than 2 seconds. whereas short is less than 2 seconds. So short GRBs, we think, are caused by neutron star mergers, and they are therefore slightly shorter in duration, usually lower than 2 seconds, but more often than not in the millisecond range of time for which they last.
Was one thing I forgot to mention earlier, which I saw just the other day, they detected the first repeating one. So the whole idea with the gamma ray burst is like maybe it's a star going supernova, or it's two neutron stars merging, and these are once-off events. So they had one which repeated 3 times.
What?
Yeah,
3 times?
3 times. So like they witnessed it, and then I think it was in the space of a few hours. It went 3 times. So that obviously we love these things because we have no idea what it is.
Yeah,
but the idea is potentially it's a star getting devoured by an intermediate mass black hole. In which case it's not happening in one go. It's like getting coming in clumps, being eaten in clumps. So like merging in clumps rather.
So that's incredible for multiple reasons, because we've never actually detected an intermediate black hole before.
No, exactly.
That's a good point.
Yes.
That's theoretical, right?
Yeah.
That's cool.
Yeah. It's great. It's like,
Wow.
so like there's levels of excitement.
The short gamma ray bursts are caused by something slightly different to the long gamma ray bursts, right? So the long gamma ray bursts, as Simon was saying, you've got this fireball model, and you've got like the jets and shock from a collapsing star forming a black hole. But then the short burst, that's caused by something different. So I have 2 favorite GRBs. The first one is the one that was detected at the same time as a gravitational wave.
Yeah,
of course. Yes. Well, that's everyone's favorite.
2017, yes. The simultaneous detection of those 2 things is ridiculous, considering how difficult it is to detect gravitational waves. And also the fact that, like you were saying earlier, they basically just turned it on.
Yeah.
And they detected it.
So a bit of background for those who aren't aware of it. We definitely covered this previously. But in 2017, there was the first ever detection of 2 neutron stars merging by a gravitational wave detector. And simultaneously, for the first and now only time, there was an electromagnetic counterpart, which means normally when you get a black hole merger or a gravitational wave merger, because they're black holes, there's no light escaping. But in this case, the resultant merger presumably isn't a black hole, or wasn't initially. So a lot of the light escaped. So we witnessed this first in a gamma ray burst, and then it cascaded through the energy spectrum. It was witnessed by SALT, observed by SALT, and various other things. Very exciting event in 2017. Everybody absolutely lost it. As you were saying, like they had sort of just turned LIGO on really for this and witnessed it. And it was, at the time, that it was calculated to be like a once in 40-year event, and it happened within like a couple of months. And now it's been 8 years and we haven't seen another one. So
Peak too soon, right? Beginner's luck. Wow.
Beginner's luck. Yeah.
But that was cool. And then that basically proved how a whole bunch of the elements in the universe were formed, right?
Yeah. Like, we ticked a whole lot of
yeah,
questions.
gold and platinum.
Like entire
and...
fields of astronomy just died that day. Tick, done.
Solved. Moving on.
ones were born.
Go get another job. And then my second favorite is boat. Boat, BOAT, brightest of all time.
Yes.
The Lionel Messi of gamma ray bursts.
Yeah, that
They're
thing.
good.
So the boat, the boat was, nicknamed the boat because it was the brightest just thing ever observed. It was in 2022, in October of 2022, and it fried some of the detectors that were used to detect.
Because it was so bright.
Yes, and it
It's
also
insane.
caused a slight resonance in the ozone layer.
What?
Yeah.
Where was I
basically-
that day?
That explains a lot.
Yeah.
It basically
I
made...
had that ringing in my ears that day.
Yeah, it's very much
2022.
it's
really
I
big
mean,
like
we
a
were
bell.
probably still in
Yeah.
lockdown at something, or some sort of.
Was that still lockdown?
I mean, we were social distancing, I suppose.
yeah.
But anyway, a ringing in the atmosphere.
That's
That's
Wow.
a good question.
The
Back
headline.
to the beginning of this episode, when we were recording in here. When did we come back in here?
Where there was a long break of 3 years.
Where we just recorded online?
Yeah. because I got stuck in Australia for a year and a half,
right,
if
you
you
got stuck in
remember, and we
Australia.
had to social distance before that. So
Oh man, yeah.
You had to teach from Australia.
I did, yeah,
For a year.
yeah.
That was my
Sure.
class.
Yes, that was your
Yes.
class that I lectured third year online
Wow.
from Australia, which was not unusual at that point because everyone had been
Yeah,
learning
yeah,
online.
yeah.
But anyway, we digress significantly.
Sorry, that
Yes.
was my bad. Yeah.
But I think we've covered GRBs
Yeah,
now.
Pretty decently.
So why don't we get back to what we used to do in here at the end of an episode, which is check in. How are you?
Oh yeah.
Yeah.
Wow.
How are you, Francois?
I'm well. Really busy with getting stuff ready for my thesis. I have something to write up at least now. Finished a little project, which I thought would take about 2 months, and it took 6. Apparently, that's normal.
That's very
Standard.
normal. Yeah.
Yeah, and I'm making ready. I'm getting ready to leave to Sutherland tomorrow. I have an observation run on the 1.9 meter telescope again, so looking forward to that.
Yeah,
I actually quite
cool.
like
Cool.
observing.
Yeah,
Yeah.
I look forward to hearing about that when you
Yeah,
come back next
sure.
time.
Yeah. I hope you get some good weather because it's been absolutely diabolical
Yes,
the
I
last
know.
week. in Sutherland.
Yeah, trust me, I know.
I think yesterday the wind didn't get below 80 kilometers an
Oh,
hour.
gosh,
It was
wow.
absolutely howling.
And Sutherland is, of course, where all the telescopes for the
Yes.
South African
Sorry.
Astronomical Observatory are based.
Probably
Dan, how are
should have
you?
mentioned that.
I'm all right. It's been a while since we've had a check-in, so I think a lot has happened. But in general, yeah, doing okay, thanks. A lot going on, as always. One of the things which is coming up, which we can feature in an upcoming episode, is it's the 20th anniversary of SALT
Yeah.
being
Yes.
constructed. So
yes.
very busy with that, getting ready for some celebrations up in Sutherland again, and yeah, getting everything in a row for that, and that'll be very exciting.
Yeah.
How are you, Jacinta?
Jinx.
Jinx.
Double jinx.
I'm well, considering actually. I had a bit of a tumble down the stairs on the weekend and have 2 bruised knees and a very bruised ankle that's about the size of a tennis ball.
How's the ego?
It's humbled.
Also
Humbled.
bruised. Yeah.
Yes, bruised ego, that's true.
Yeah.
But I didn't break anything, which is a miracle, so I'm very grateful for that.
That is
and
great.
just appreciating how well most of my body works most of the time at the moment. So yeah, but just moving slowly.
That's great.
Very slow. I'm using an umbrella as a walking stick.
Look a bit like Nanny McPhee.
Yeah.
Or what,
Mary
Poppins, yes.
Oh, just a spoonful of sugar. Yeah.
Yes. So
Let's
you're
not get
saying
into
that,
singing.
do I get to eat chocolate all day? That's what I'm hearing.
Totally.
Yeah.
Fantastic.
Yeah.
Fantastic.
Oh, I forgot to
Even-
mention, I also just came back from my first ever conference overseas. which
Oh.
was incredible.
Where'd you go?
Hamburg, Germany.
Oh, nice.
Tell us about it.
That was great. It was actually I met Simon there.
Oh,
Come
cool.
to think of it.
This really should have
Yeah.
been mentioned earlier.
Yeah, probably. Yeah, I met Simon at that conference. It was about the Black Gem Array telescopes, which we will talk about in a future episode. But they are very, actually, really to do with what we were talking about, because they are designed to detect the optical counterparts to gravitational wave emissions,
Oh, cool.
which we will
Hmm.
probably discuss in a
All
future
right.
episode.
Well, the timer on our
the
on our camera is about to go off, so we better wrap this up.
Yes.
Should we do a
Um,
final wave?
All right. So that's it for today. Thank you very much for listening, and we hope you'll join us again for the next episode of The Cosmic Savannah.
You can visit our website, thecosmicsavannah.com, where we will have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on X, Facebook, and Instagram at Cosmic Savannah, and now also on TikTok. Apparently, I don't even know what that is. That's Savannah, spelled Savannah. You can also watch the podcast on YouTube with closed captions, which can be auto-translated into many different languages, including Afrikaans, isiXhosa, and isiZulu.
Special thanks today to Dr. Simon de Vet for speaking with us.
Thanks to our audio editor, Nick Rushton, our podcast manager, me, our social media manager, Sumari Hatting, our assistant manager, Kashifa Saluji, and our other awesome interns.
Sisi Shabane, Karaba Rantwane, Kamagelo Letswalo, Tato Nombeu, and Charmaine Mbuti.
Thanks to today's incredible videographers from Visual Pill Productions. They are Rizwana Saluji, Salvador Marcel, and Reese Bryce. Also thanks to Susie Karras for graphic design, and Brian Mashamola and Michal Werchek for photography.
We gratefully acknowledge support from the South African National Research Foundation, the Square Kilometre Array Observatory, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, the the University of Cape Town Astronomy Department, and the One Button Studio at UCT.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcast, and we'd really appreciate it if you could rate and review us and recommend us to a friend.
We'll speak to you next time on the Cosmic Savannah.
When are you a doctor?
I don't know.
Every episode. It's going to happen every episode.
It takes a while.
You haven't started your PhD yet.
No.
You're still in your master's.
I'm stuck in masters.
You should say, and not a master.
Yeah, still not a master. Not even a doctor.
Just a bachelor.
Yeah.
Hello, everyone.
Hi. You know,
sounded
we should probably
sarcastic.
look at the camera at some point, right? When
No.
we say hi.
No, we'll do it in a minute.
No, yeah.
When we announce what we do.
All right, let's start that again.
All right.